This grid represents the core assumption of standard quantum mechanics. When building an n-qubit register, theory states it occupies a continuous space. Every time you add a qubit, the available degrees of freedom multiply outward, creating an exponentially expanding matrix. The entire field of quantum computing treats this formal mathematics as literal physical reality. The hardware engineering paradigm operates on the premise that this vast exponential continuum is physically available inside the machine at an arbitrary resolution. Observe the nested infrastructure of these dilution refrigerators, the miles of high-frequency cabling and multi-stage cooling needed to stabilize just a handful of qubits. Standard theory views this hardware overhead as a purely practical obstacle, a matter of engineering noise and isolation. Billions of dollars are currently riding on a singular premise. If we can isolate the system and suppress the noise, the physical universe will automatically grant us access to that infinite mathematical scaling. The TCGS-SEQUENTION framework proposes that standard quantum computing might be mistaking a highly successful mathematical map for the physical territory. The mathematical models point towards an endless infinity, while the actual physical universe enforces a hard, unyielding structural barrier. We define this boundary as projection bandwidth. It is the physical universe's strictly limited capacity to instantiate complex, highly distributed quantum states. This aligns directly with physicist Tim Palmer's rational quantum mechanics thesis. Palmer argues that physical reality enforces a finite information capacity, a strict upper limit known as N-max. If the physical territory is finite, massive quantum algorithms will eventually hit a hard physical wall. No amount of error correction can unlock space that the universe simply does not possess. To be clear, continuous quantum mechanics is undeniably successful at small scales and for isolated states. It predicts laboratory results with exacting precision. The TCGS-SEQUENTION framework explains this success through what it calls the shadow calculus. Hilbert space is an exceptionally powerful operational tool used by observers to organize amplitudes and phases, but it is still a shadow cast by a deeper reality. The mathematical continuum we use in our equations belongs entirely to the observer's map. The physical reality it describes originates from a non-temporal, multidimensional source called counterspace, which projects specific, constrained states into our observable three-dimensional world. Assuming that every variable in the math exists physically is a category error known as ontological inflation. A model can be highly predictive in its valid domain without requiring its infinite variables to actually exist in nature. The predictive success of Hilbert space at 10 qubits does not guarantee its physical instantiation at 1,000 qubits. To visualize this limit, we look at Palmer's discretization of the Riemann sphere. Instead of a continuous curve of complex numbers, the state space is constrained by a granularity parameter, L, which forces the geometry into a faceted, finite surface. Standard quantum mechanics is recovered as a singular continuum limit. It is an idealization that only exists if the L parameter approaches infinity. By imposing finite rational admissibility constraints, this model actively eliminates specific counterfactual quantum bases. Entire coordinate regions become mathematically impossible to physically occupy. Standard decoherence describes information leaking into the environment. Palmer's constraints describe something more absolute, states that the physical map is geometrically incapable of supporting. If physical reality requires a finite parameter L, the standard continuous quantum state is strictly bounded. It cannot physically occupy every conceivable coordinate in space. This chart visualizes the exact intersection where hardware fails. The steep curve represents the 2 to the power of n exponential demand of the formal quantum state, while the flat line tracks the strictly linear growth of physical, bitwise hardware capacity. The point where these two lines intersect is N-max. This is the boundary where the exponential algorithmic demand permanently exceeds the finite descriptive capacity of the hardware. Below this boundary, quantum operations function exactly as theory predicts. Low entanglement states, single qubit rotations, and simple stabilizer circuits survive because their demands stay firmly under the threshold. Even complex systems can operate successfully if their algorithms remain trapped in effective subspaces or tensor network-efficient structures. They never stress the ultimate limits of the projection bandwidth. The true pressure appears during fully distributed maximal state space algorithms. These protocols demand sustained phase relations across the entire exponential continuum, testing the hardware's ultimate projection capacity. The physical universe strictly caps quantum operations that require more state-space resolution than the linear hardware shadow can actually project. This reframes our understanding of Shor's factorization algorithm. It is a global algorithmic stress test of Hilbert space access. To achieve its calculated speedup, the quantum Fourier transform inside Shor's demands sustained, perfectly coherent phase relations distributed across vast computational registers. Pushing those structural requirements to their limit inevitably triggers N-max saturation. This is a map boundary event, precise, analytical. This event is distinct from gate drift, calibration errors, or thermal noise. It is a structural projection failure built into the geometry of reality. A massive quantum computer operates as a cartographic instrument. It maps the absolute physical limits of the shadow projection. Every additional qubit added to a maximal algorithm acts as a probe, pushing the hardware further against this invisible reality boundary. A reproducible failure at this scale reveals the boundary of the shadow. It marks the transition from hardware defects to the discovery of reality's absolute resolution limit. This chart details the specific empirical signature required to prove the existence of an N-max projection boundary in laboratory scaling studies. Standard hardware noise presents statistically, gradually degrading the system's performance. The map boundary event creates a rigid, geometric horizontal saturation plateau. This projection bandwidth saturation would persist completely unaffected, even as local error correction and cryogenic cooling continue to improve. To identify this boundary, the anomaly must scale specifically with the algorithm's distributed Hilbert space demand, rather than correlating with random, local hardware faults. True scientific verification of the TCGS-SEQUENTION framework requires isolating this exact geometric failure from correctable hardware inefficiencies and confirming it across entirely different hardware platforms. This reveals the two sides of this physical boundary clearly by contrasting the offensive limitations of Shor's algorithm with the defensive success of quantum cryptography, specifically the BB84 protocol. BB84 succeeds entirely by exploiting the finite map's restrictions. It relies on chart incompatibility and measurement disturbance, ensuring that any unauthorized attempt to read the quantum state leaves a detectable physical trace. This theoretical boundary is the driving force behind the current global transition toward post-quantum encryption standards, governed by institutions like NIST. BB84 functions because it operates within the strict limits of the quantum map. Shor's algorithm threatens classical encryption by demanding an impossible, infinite global continuum to break the math. This reveals the danger of mathematical reification, confusing our predictive coordinate systems for the underlying substance of the universe itself. The mathematics of Hilbert space provide an excellent map for isolated quantum states, but stopping the confusion between that map and the physical territory is the only way to understand the true constraints of quantum technology.